Hi everyone. 4.2 resultant magnetic field produced by current carrying conductor. Okay, for 4.2a, we learn how to sketch resultant magnetic field diagram at a point. When a current flows in the conductor wire or coil, the magnetic field will be produced in the surrounding space. The magnetic field produced at any point in the space is denoted as B. It is a vector quantity. SI unit is Tesla or symbol T. Generally, there are three types of conductor wire. That is long straight wire, circular coil, and solenoid. Okay, let us go one by one for these three types of conductor wire. Right. For current carrying conductor in a long straight wire, at a perpendicular distance r from a long straight wire carrying current I, the magnitude of magnetic field B is given by B equals to mu naught I over 2 pi r. Okay, where mu naught is 4 pi times 10 power of negative 7 Tesla meter per m. Right? Okay, so from this long straight wire, this is the direction of the current I. Okay, in order for us to determine the magnetic field, we can use the right hand rule, the right hand rule grip. Okay, so this is the direction of your thumb. Okay, and this is the direction of your curl finger. This is from the upper view. Okay, in this picture we can see that this is the cross here. That means that the current is into the page. Okay, so current into the page, and then when we curl our hand with finger, we can get the magnetic field would be clockwise. Okay, the direction of the magnetic field would be clockwise. Okay, you can see this. All right, this line, the line closer together here, shows that the magnetic field is stronger, compared to these lines. Okay, where the lines further apart, that shows that the magnetic field is weaker. Okay, the direction of magnetic field B is given by the right hand rule too. That is the right hand grip rule. Okay, so from this right hand grip rule, your thumb will point along the direction of the current, whereas your fingers, you curl your fingers around the current carrying conductor, and you can get the direction of the magnetic field. Okay, if the current upward and you curl your fingers here, you can get that the magnetic field will be anti-clockwise. Okay, right. So what will happen if the direction of the current downward? You just reverse your hand here, put your thumb here, you curl, so therefore your direction of your curl fingers will be clockwise. Okay, right. So let's take a look at this diagram to show you, to explain you more clearer what will happen when you curl your finger around the current carrying conductor. Okay, example here, you got this. Okay, so current upward. Okay, when current upward, you curl your fingers. Okay, right. This is your thumb to show the current. The curl fingers, okay, to show the direction of the magnetic field. Okay, so from this diagram, you can see that on the right side of the wire, the magnetic field would be into the pitch. So we denote it as cross here. Okay, whereas at the lower point here, the diagram shows that the direction of the magnetic field on the left side of the wire. Okay, so we show that the thumb upward. Okay, that means the curved finger will point outward. Okay, so it will be denoted by the dot. That means the magnetic field is out of the page perpendicularly. Right, let's take a look at the circular coil. For current carrying conductor in a circular coil, okay, is given by the formula B equals to mu naught I over 2R, where mu naught is permeability of free space, that is 4 pi times 10 to the power of negative 7 Tesla meter per m, where r is the radius of the coil. So this is the general equation of the magnetic field strength at the center of the circular coil. For a circular coil consisting of n turns, radius of a circular coil r, and carrying current I, magnetic field at the center is given by B equals to mu naught n I over 2R. This is the magnetic field pattern generated by a flat coil. This is from the overview, from the top. Okay, and this is the pattern of the magnetic field. Okay, when we see from the side. Okay, take a look here. This is the current flow into the page and the current flow out of the page. Okay, so if out of the page, that means this is out of the page, so this one. Okay, so on the left side, it's the same here. So the magnetic lines of forces, okay, so will be anti-clockwise. Okay, whereas for the right conductor here, okay, the coil that goes into the page, the magnetic field will be clockwise. Okay, the direction of the magnetic field is given by the right hand rule 2. Yeah, for the coil can also, okay, be determined using the right hand grip rule. Okay, how can we use this? Okay, we know that at each side of the coil, okay, for the current out, that means current into the coil, okay, the direction of the magnetic field will be anti-clockwise. Whereas for the current out here, right, so it goes into the page. If we put a page in the middle of the circular coil, so this one is into the page, we can determine that the magnetic field would be clockwise. Okay, so that means at the center we'll get this kind of pattern. Okay, so from this pattern we can determine the north and south pole. Okay, we can determine this is the north pole and south pole also by using our right hand grip rule. Okay, so this your thumb would be your magnetic field B, that's it for the north here, and your curved finger, okay, this one should be determine the direction of the current flow, from here to here. Okay, so the curve upward, therefore you got north here, you got south here. Okay, by using your right hand grip rule. Okay, so the curved fingers determine the current. The thumb point would be the north pole. Okay, so this is for circular coil. Right, next we go to the solenoid. Okay, what is solenoid? A solenoid is constructed by winding a long wire into a tight coil or helix with many circular loops. Okay, This circular, it also deals with circular coil, yeah, but that is more than one. Okay, so the magnetic field is given by, at the center of the solenoid is B equals to mu naught N I. At the end of the solenoid, B equals to half mu naught N I, where N equals to, this is N, the number of turns divided by the length of the solenoid. Okay, and this mu naught stands for permeability of the free spaces. I is for current, N is the number of turns per unit length, N is the total number of turns, L is the length of the solenoid. Okay, so this is what it should look like. Okay, the current flow into the solenoid. Okay, and this is out of the solenoid. Okay, so you can see here, this is the current into the solenoid. Okay, so your curved fingers, this is your curved finger will be upward. So your thumb should be this way. So this is the north, okay, and this is the south pole. Okay, right. Okay, I can see here, this is if it is the current downwards. That means current flow into and out here. This one, current flow into and out here, right? So this is the direction of current. So in order for us to determine the north pole, we have to determine the direction of the current first in the solenoid. Okay, so automatic, your thumb would show the north pole. Okay, right. Let's take a look at the example. A long wire X carrying a current of 50 amp is placed parallel to and 5 cm away from a similar wire Y carrying a current of 10 amp. A. Determine the magnitude and direction of the magnetic field strength at a point midway between the wires. 1. When the current are in the same direction, and 2. When the current are in the opposite direction. Okay, and B, when the currents are in the same direction, there is a point somewhere between X and Y at which the magnetic field strength is 0. How far from X is this point? So, okay, we have two questions here. The first one, we have to determine the magnitude and the direction of the magnetic field at the midway between the wires. And the second one here, we are given that the current are in the same direction and we have to determine the position where the magnetic field strength is 0. Okay, okay, let's go. Right. First, we take out all the information given. We know that the current for X is 50 amp. Diameter, that is the distance between the current carrying conductor, that is 5 times 10 power of negative 2 meter. This is the current of Y, that is 10 amp, right? Okay, so this it should be the diagram. Okay, first of all, before you do anything, you have to draw the diagram. So it is easier for you to understand the situation of the problem. Okay, now determine that when the current are in the same direction. So this both I of X and I of Y in the same direction, that is upward. Okay, right. Using the, okay, when we have determined the direction of the current, we can determine the direction of the magnetic field at the midway of the two wires. Okay, right. So for I, if you put your thumb upward, you curl your finger, that means your finger at this point, that is at the middle, would show you to the page. Okay, Whereas for IY, the thumb upward, you curl your finger using the right hand grip rule. Okay, so your magnetic field would goes outward here. Okay, right. Or when we see from the top, okay, so this one is out of the page dot. Okay, so current out of the page, so the magnetic field for X will be upward and magnetic field for current Y will be downward. Okay, then we just substitute. Okay, at the middle, and that means we have the distance given 5 times 10 power negative 2. Since it is at midpoint, that means half of the distance between IX and IY. That is 2.5 times 10 power of negative 2 meter. By using the equation of magnetic field at any point near straight wire, then at point A, magnitude of Bx, okay, you have to determine the Bx, that is mu naught Ix over 2 pi Rx, okay, so we just substitute, okay, punch into your calculator and you should get the Bx should be 4 times 10 power of negative 4 Tesla. Okay, is it enough? Not yet. We have to determine the result. Okay, right. So you have to determine that the direction is into the page or upward. Okay, since it is a vector, yeah, when you find the magnetic field, that means you have to uh, write down, yeah, the direction. In this case, it's either into the page or upwards. If you draw the diagram for the second diagram, that means you must say it is upward. If you draw like this, that means it is in, for the first diagram, that means it is into the page. Okay. So then we have to determine the magnitude of B of Y. So just using formula By mu naught Iy over 2 pi Ry, we substitute all the value for Iy. Then you got By equals to 8 times 10 power of negative 5. Okay, then we need to, okay, determine the direction that is out of page or downward. And then we have to total the magnetic field at point A, that is BA is equal to BX plus BY. Okay, so since BY is out of the page and we take it as positive, when it goes into the page, we take it as negative. So we got negative Bx plus By. Okay, so BA negative 4 times 10 power negative 4 plus 8 times 10 power negative 5. Okay, this is considered downwards as positive. Okay, upward as negative. Okay, so that means we got the negative 3.2 times 10 power negative 4 Tesla. That means the direction is upwards or into the page. Okay. Okay. For question 2, when the current are in the opposite direction, we redraw the diagram and, okay, this time we put that current in the opposite direction. Okay, so we can get that the both magnetic field will be on the same direction, yeah, either into the page or upward. Okay, so by using the equation of the magnetic field, we just substitute. Okay, we got the same number, that means for, okay, the direction into the page or upward. Okay, for By, we got 8 times 10 power of negative 5, yeah, into the page or upward. Okay, so for the resultant, okay, yeah, that means B of x plus B of y, since both are upwards, okay, we take that upward or into the page as negative, so both negative, negative, so we got negative 4.8 times 10 power of negative 4 Tesla, okay, that means it is, direction is into the page or upwards. So when we have the negative sign, that means the magnetic field is into the page or upwards. Okay. Okay. Actually, this is only for to show you the direction. Okay. Right. Next, we have to determine the magnetic field where the magnetic field is 0. Okay. When the current are in the same direction. Okay, we redraw the diagram like we did before. Right, in this case, we don't know the exact where should be the magnetic field because you are to determine. Okay, let's say the Rx equals to R. Okay, Ry is D minus R because we know that from Ix to Iy, that is D. If this is R, that means D minus R. Okay. So, since the resultant of magnetic field at point C is 0, therefore BC equals to Bx plus By. That is, one of it must be in the same magnitude but opposite direction. Yeah? Since BC equals to 0. That means magnetic field at point C. So that means Bx is equals to By. Okay. So we know that Bx and By, okay, using the formula, we're using the relation Bx equals to By, that is mu naught Ix over 2 pi Rx equals to mu naught Iy over 2 pi Ry. So this mu naught 2 pi can be cancelled out, okay, and we just leave out the current of x, current of y, r, and d minus r. So we substitute with the value that we have, so we got the r equals to 4.1667 times 10 to the power of negative 2 meter. That's all for 4.2. See you then on 4.3. Thank you.